Okay, let me see. Let's share.
Something start. I guess now you can share your screen. There should be a share button on below. Okay.
Yeah, I think all I need to do is.
Yes, now we can see your screen, Nicholas.
Great. I will. If I just hit present, I guess it'll figure it out. Except I have this little dialog box at the bottom. Push that out of the way. Can you see the slides?
Yes.
Great. Well, then I think I have about half an hour to talk. So that's great. What I want to do today is actually a fairly simple talk. It's a talk of two halves. I'm going to speak about first a framework we've developed called Flower that really emphasizes the ability to evaluate these federated learning algorithms in more realistic settings. We feel this is a gap in the current methodology that we see from the literature, whereby people are developing these methods and are not sufficiently accounting for the distributed system resources that they use and the various sort of complexities that come with it. And then at the very end of the talk, I'm going to focus on how you can use this tool and how we extended it to assess the carbon footprint of these federated methods as that sort of emerging sort of dimension to machine learning in general, assessing not only energy, memory, accuracy, but thinking about societal impact of using these techniques. So great. Well, before I begin the rest of the talk, I really want to just highlight this is a lot of systems work that is, and so it falls on the shoulders of postdocs and students. And so I've just highlighted their images at the bottom of this slide here. Okay, so let's begin. I understand this is more of a general sort of workshop, so I think it's fair to start with just a quick, 1-minute summary of what federated learning is. This is a method by which we can train machine learning models using data that is stored locally. So conventionally, to train a model, you would need to get your labeled data, collect it together centrally, and then run some training algorithm over the top of that data to produce a model. And there's a few downsides with that. And one of the main ones that federated learning seeks to address is the issue of privacy. By centralizing the data, everyone who's participating in the system needs to provide labeled data centrally. So, for example, there could be sensitive information like images, there could be speech in there, there could be medical records, and essentially federated learning seeks to stop that being required. The model you could imagine is that users leave their sensitive labeled data locally on the device, and then through federated methods, a model is trained without any of this data ever having to be aggregated. And this is what the diagram is trying to illustrate here. You start off, if you look at the devices, each device has some labeled data. They are going to be exposed to a small part of the data set, the ones that are the part of the data set that the user itself has exposed him or herself to or provided. And then locally, the devices will perform gradient descent to generate gradients that are model updates that inform the model on how it should change its weights to be better and more accurate on the basis of just the data that it sees. And under federated learning, it is these model gradients that are centralized, that are then aggregated in the cloud, such that they are then applied to a central model. The model is updated independently with individual gradients coming from individual devices, and then that allows you to produce a single model that could then be distributed to the devices again in terms of being revised and updated. So that's the general principle of federated learning, and then you'll see it being applied in a variety of domains. So an example would be a robot, where you'd need to have it maybe adapt its perceptual engine to the domain of images that it sees locally. So, for example, cars might have a certain type of look, roads might have a certain type of look for the area in which it operates. You can do this through federated methods without having to upload all the data, which can be quite considerable. where federated learning is used, the largest examples of federated learning being used today currently are being run by Google. They have systems that do, for example, keyboard prediction. So these services that try to predict next word or try to realize which character sequences you're typing. And then these models that drive these keyboards are trained using federated methods. And then finally, a classic example that people point to is just the ability of federated learning to support the training of an aggregate model whereby you are based on information that you don't necessarily want to have shared between entities. So you might have a hospital benefiting from records from maybe a school, benefiting from records from maybe an employer, but under no circumstance do does the data ever have to be co-located for the model to be updated. So there's some motivational reasons why people want to use federated learning and its characteristics. So that brings me to the heart of this talk. Again, as I mentioned at the start, we're going to focus on describing for you a new framework that makes it very easy to evaluate federated learning methods in a more realistic manner. And then I'm going to tail off the end of this talk with some early results on just how carbon and environmentally friendly these methods are as opposed to data center ones. I have to move fairly speedily through the framework, so if there's any details you want to find out about it, you can either ask questions or check out our paper on archive. And now, so why is it that we'd want to be able to evaluate these methods in a more realistic setting? And that is because if you look in the papers that are being produced today on federated learning, there's a limitation to how people are typically evaluating them, and that is that they would often use an evaluation method something like this. This is maybe perhaps an exaggeration, but it shows you where the concept of federated learning is that you're going to have a huge distributed system that's very complex and interesting, and of course all these complexities that come from its design and operation. But when it comes to evaluation, far too many of the papers are using a method like this to evaluate it, where you might have just a few nested for loops running on a relatively powerful machine where each element of the loop stands in for each individual client. Now, obviously, evaluating under this sort of circumstance will never be able to capture the complexity of a real distributed system where you have to deal with things like networking and wireless fluctuations, compute heterogeneity, so different devices have different amounts of compute available to them, memory availability and differences between different devices. After all, you could potentially have federated participants in terms of clients ranging from an embedded camera that might be very low end up into a flagship smartphone. So you somehow need to have that type of difference accounted for inside the clients. Is energy and scale. Now, one note on scale, to further sort of look in terms of the limitations of how people were evaluating their algorithms, we did a bit of a literature survey in terms of scale. And so this is a survey of around 100 papers that we saw from the last couple of years, taken from Google Scholar. We looked at each one and saw how many federated learning clients are they evaluating their algorithms under. And so this is a histogram. So the number of papers at the different bins of client levels are shown. And then you'll see that a majority of these papers are evaluating their system at 100 clients or less, even though the motivation for these systems and the target that they want to be able to pitch their algorithms for considers a design space that's more like in the millions. And I would point out that even though that you might see systems here that are using 500 clients, 1,000 clients, this still includes evaluation strategies that are just simple simulations or even just nested for loops. We have a lot of different elements within a single machine looping around each other. So it's not like these are authentic clients at all either. So you'll see that there's that in terms of academic literature, there's an understudy of these systems at large scale and under realistic settings. So this brings me to Flower. Flower is a framework that sits on top of conventional deep learning frameworks. So this is a framework that would sit on top of, for example, TensorFlow or PyTorch. We designed that deliberately because we envision that a majority of these systems are likely to be heterogeneous in terms of also the frameworks. So it's likely that you'll have different types of frameworks running on different types of devices. Because different devices will have certain types of capabilities, and so it's obvious that the framework's often going to also vary as well. What we also did was build in a federated learning system where, as a first-class citizen, we consider the ability to do sensitivity analysis on these different types of system dimensions that we argue as being very important. I'll just quickly run through the framework, but essentially, because it's relatively boring software details, but essentially you can connect up any training pipeline that you've coded already. So you might have some sort of model that you've slaved over to make sure it works really well. It has high accuracy. If you've done that, chances are it'll be one of the popular training frameworks, and we allow you to directly just use those existing pieces of code. So essentially with Flower, you can federate any type of model that you've already got to train successfully on one device, on one sort of GPU. We also have these SDK clients that allow you to build out a Flower client in a variety of different languages that will map to the different devices and the languages they natively support. Because we understand also that not only is evaluation under realistic settings, but also systematic reproducibility and comparisons to other types of techniques is also an important dimension of this sort of realistic evaluation. We have implemented a series of baselines that are commonly compared to in the literature, things like Fed average and latest, more recent ones such as Q-Fed average that can act as baselines for when you develop your own federated learning approach. And then similarly, alongside this, we provide examples, benchmarks, and data sets that, again, allow you to normalize your comparisons in a more systematic way. And then finally, probably the most important part of the framework are these tools on top, which allow you to simulate different types of conditions. One of the big important missing pieces is allowing researchers to easily scale up their experiments. So what we did was we've included functionality in Flower where it can easily interface with cloud providers. So people like, in particular, we've implemented out the Amazon AWS components, and what they do is they will start and stop instances on AWS so that you can simulate easily by just changing a few configuration lines, 1,000 different clients if you want. You can also decide if you want to have clients be very realistic in terms of being independent actual systems, or you can have multiple simulated clients mapping to one physical system as well. So that's an important component of being able to do realistic scale. And then in terms of the type of heterogeneity in the conditions, we include network simulators, so you can vary the amount of bandwidth or the types of network behavior you see. You can also wire in estimators of energy for the different clients, so you can see how that might be fluctuating across the clients when you do your experiments. I just want to kind of, I want to sort of move through this material fairly quickly. Just want to get to the summary, which indicates that you can use Flower to scale your experiments up when it's backed by a cloud provider like AWS, do sensitivity analysis across network and wireless compute and memory. And importantly, I've spoken about it in the sense of being able to do simulations of large amounts of experiments where you can use real devices or simulated ones. But it's also possible to do application level research using the system, whereby you can build a fully functional federated learning application and study dimensions in that sort of layer of the stack as well, if needed. And on the right-hand side, you'll see the configuration scripts that are used to configure the system if you just want to get up and running very quickly. So for example, you can point to a model like ResNet 50, which would be backed by some training scripts you've written. You can indicate how many different clients, say number underscore clients is 10, and it'll solve everything for you. And we like to say that, within one line of code, you can get your federated learning system up and running. And we think this would be a big driver in terms of doing research, because it's one of those areas where without these types of experimental support, researchers can get bogged down in having to implement a lot of different components before they actually get to their research. So we hope that this can really accelerate people to explore sort of more algorithmic and technical areas of the equation, and not worrying less about having to have all the nuts and bolts working. Let me now run through 3 different experiments that we think are important for indicating how our flower is able to produce some of these experimental support needs. Let me focus first on the left-hand side here. And what's interesting is that we're using these 2 experiments to look at the scalability and robustness of this framework. For large-scale experiments and models that use a lot of data and that are relatively complex, it's not surprising if federated learning is a lot of devices working together, with each device participating and with each device being relatively low in its computational power. And so here we have an experiment which we think is probably the first time ImageNet, it's a well-known large-scale machine learning dataset, has ever been actually trained. So are using federated learning. And so this is top 1 accuracy, where we see it gets to around 80%, but after 2 weeks of operation. So we have our flower framework working for 2 weeks before it can converge to its model. If I look on the right-hand side, let me show you another example of flower scalability. This is an experiment where we varied the number of clients, taking it all the way up to 1,000 clients. So this is much larger, because each client, much larger than what you see in the literature right now, because most of the times you see people hitting these sort of figures in situations where, again, they had these sort of nested for loop styles of evaluating client behavior. We can see that Flower is able to handle it. Now let me show you 2 experiments, or actually maybe just 1 experiment, that points to the issue of diversity within your client pool, and why it's so important to authentically capture all the different types of system resource issues. On the left-hand side, we have a figure here. Again, this is all done using Flower. On the y-axis is training time. The x-axis, we have 2 different categories of federated learning client pools. The setup of this whole experiment is identical. It's using the Fashion MNIST dataset. We have 50 clients, and with your every round we have 5 clients participating. But blue and red show dramatically different durations of training. Now, the only difference, though, is that within that small pool of clients, we disabled the GPU of one of those clients. So you had basically one client that was crippled, that was much slower than the others. And then we looked at what happened to the overall system performance of the federated learning system to actually train. What you can see there is that there is a huge increase of 3.5 times in terms of the length of time it takes to train, when only 1 in 50 has a significantly slower computational capacity if they're fully participating within the federated learning algorithm. And so you can imagine if you're out there designing federated learning algorithms and not evaluating your setup to account, for example, potential heterogeneity, which easily could occur in real life, you'll be missing out on understanding the true behavioral system in these types of settings. Let's look at another example in terms of real-world types of behavior. Obviously, federated learning devices are not always going to have very high bandwidth connections. And yet, most of the experiments you see, if they are done on real devices, are over wired connections. So you might have, for example, speed like 1,000 megabits per second. In actuality, in real federated learning systems, they often will be connected using things like 4G. Now, 4G might have a speed of around, say, 30 megabits per second. You can see here the length and training time. It jumps up to 2.1 times when you simply have this reduction in network speed between your devices. So this is two key results I wanted to show you that, again, they were all generated using Flower. They show Flower to be able to scale up very well to the types of scale that we think that these algorithms should be compared under. And the second result there was really talking about how relatively small amounts of system realism introduced into the system can result in these large reductions in system efficiency. We looked at that, and then we said to ourselves, now how can we push the system even harder to show some results that folks haven't seen before? And in particular, in the world of centralized training, there has been recent sort of angst about just how much carbon these systems are actually producing. So, for example, there's this well-known NLP example where the state-of-the-art in NLP modeling, natural language processing, to train that model will actually cost you the same amount of carbon as a family of 3 living for a whole year in the States. And so that's probably one of the most extreme examples you can have. But what we thought was important is that it was not until much later in the story of deep learning that people start to think about this problem. And so we felt that as federated learning is an emerging paradigm, we should also start to study its properties in terms of its carbon footprint. Now, I won't go through the details, but essentially doing this analysis involved using Flower to generate very authentic traces of how much resources it would take to train various types of models. And because we could believe on that sort of level of, we could believe that because those outcomes were very realistic, we could then build a secondary carbon model that would do things such as assess how much energy is being used and understand what would be the carbon that would result. The model takes into consideration 2 main factors: the location of country, because how electricity translates into carbon is usually impacted by how the energy is being generated. And second, we wanted to be able to compare against data center scenarios. And so we needed a model that could model both the key factors that influence data center generation of carbon. For example, cooling is a huge one. Because cooling is such a big factor in the case of GPUs, how efficient the cooling is, how much energy it costs, what's the ratio between the amount of GPUs you have and the cooling you require is a big factor on the carbon efficiency of a data center. And we similarly had to do the same sort of things for the large grain factors that affect federated learning. And so one of the big differences is that it doesn't need cooling like the data centers do, but it will face carbon emissions related to the wide area data transfers that must occur between devices that participate. So we need to model that in there too. So you should look at our archive paper if you're interested in more of these details. I just want to point out the big factors. And then this is only really a preview of the types of things you can do with this system, but I want to walk you through WAIN analysis. And keep in mind that the study of carbon emissions for centralized deep learning is only just beginning. And so we're only just beginning to have a sense of what these types of centralized training models behave like. And so this is very much, we believe, the first time that this type of phenomena has been studied under the context of federated learning. So what I have here is a single result. I want to walk it through for you. This is for training a ResNet model under CIFAR 10, where we're going to just take that model up to 60% accuracy, and we're going to train and compare the carbon of a federated learning system against that of a data center. The data center we're comparing against is just a single, very high-end GPU. So this is a V100 GPU, and we're going to ask this data center GPU to train against and compare its carbon emitted against that of a federated learning system that's fairly high-end. It's a collection of NVIDIA Jetson Xavier NX devices. So these are fairly high-end embedded GPUs. You might find them in robots, or you might find them in sophisticated smart cameras to do computational locally. We're going to ask a network of these devices. I think it's a pool of 50, but only 5 clients are used per round. They're going to train a model that does object recognition under CIFAR 10, and we're going to analyze the carbon emission. And what we see is that federated learning methods it's centralized methods result in 1.7 times more carbon emissions than the federated learning version. And so essentially federated learning, in this analysis at least, is much more carbon efficient than training models in data centers. Of course, your mileage will vary greatly depending on the models, depending on the speed of your computation, the efficiency and the power of the edge devices will affect this a lot. But this is an interesting first result that indicates that federated learning can be a lot more environmentally friendly than centralized learning for certain situations. And when we tease back some of these results, for example, if I highlight this figure on the right, it indicates and it teases out what's going on here. Essentially, per epoch, and epoch is the model being trained through every single image in the data set. In this case, that's one epoch. And so essentially, you would complete multiple epochs as you reach certain levels of accuracy. The federated learning, because it doesn't need things like cooling, because the devices are fairly low power relative to the compute they offer, has a much lower carbon footprint gradient to epoch. And that's the blue line you see. Then the data center against the V100, even though the data center GPU is able to produce much faster results. So it's able to get the model up to 60% in just 2 epochs. But because its gradient is so steep, it uses a lot more carbon. Now, federated learning takes a lot longer, takes 8 epochs before it converges to a 60% accuracy level. So there's a time and latency issue there, but it's in terms of carbon emission, it is much lower. So we think this is probably the first time this type of result's ever been shown. I'm mainly showing it also to show you the power of building on top of Flower and how you can use really authentic, accurate types of results analysis of federated learning systems. And then we've pushed it into a place where we can study now these algorithms because we have these carbon footprint emissions. We can study these algorithms in brand new ways where we're not thinking about necessarily the usual metrics like energy, accuracy, memory consumption, but societally important types of factors. And we can think to ourselves, how could we generate learning algorithms that can optimize for example, carbon footprint rather than things like latency. So that is all I had time for today. I'm happy to take questions, and I hope it's been interesting to you all.
Thanks, Nick. Thanks a lot. And if someone wants to give a question, you can just open the microphone, or if you are, I don't know, don't have a microphone, you can also type just in the chat the question, and I will read it loud. So in the meanwhile, while you think, I actually do have 1 or 2 questions for you. So first, the first is not a question, it's just one thing that I said that I want to highlight is that I really appreciate the effort for the integration with existing code, because I think this will be like a key feature for people who want to use it, and scientists, but also for companies. So I guess that this is really one key point.
Thank you. Thanks
for your framework. And instead, I have one question is general about your strategy that you use. Can you spend some words about the strategy used to manage the fairness and unfairness in the model?
Oh, and what's your definition of fairness?
I mean, in training data, there could be some underrepresentation of some labels, or depends, of course, of which kind of learning you're doing. But and since you don't actually transfer the data, so it could be actually really also hard to understand if the final model is maybe it's good in terms of accuracy, but what about fairness, that maybe it will perform really bad on some other things, since you don't have the training data in your own data center.
Right. So I understand. So one of the this sort of is more a general problem within federated learning. It's the issue of data partitioning and how it cannot be, sometimes is sort of very unevenly distributed between the nodes, and therefore you can't really believe the gradients, or the gradients are not representative of dimensional batches. And so we haven't done anything specifically to address this problem, other than realize that there are situations where the learning would just be degenerate and not test under those cases, and also use existing techniques to just cope with them the best they can. So, for example, I think all of the experiments they showed use fed average, and so there's nothing specific in that to cope with that problem that you're mentioning. But other than you need to understand essentially that if you set up the learning in a situation where there's too much imbalance, or for example, not every class has an example on a certain client, that it's not going to work, essentially. But yeah, what you spoke about is a really big problem for federated learning. You have to somehow control the conditions, or maybe, you have to somehow control the conditions for it to work, in a sense.
Okay, thanks. I see that there's a question from Andre Bondi. I'll read loud. So he's asking, in the example with the GPU disabled at one node, does each node communicate with all the others? Are the others dependent on it? Is the dependency symmetric among all nodes, or is there a central server sending data?
Oh, so I think what is, in a way that we probably picked that as a, what is happening is that it's a straggler. So the other nodes are waiting for it to provide its updates, and it is much slower, so everything takes longer. And so you could introduce different methods to overcome that problem, and that some of these have been proposed in the past. But that is showing you what basic federated learning would behave like in that situation. So I think the operation, the setup there is that you will want to have a contribution from that slow node, and you'll wait for it to eventually result, and that's why you get those big jumps in training time. And that kind of speaks a little bit to the fairness question that you asked, Luca, whereby often you might have slower or fast devices, and unless we have methods that are able to sort of mask and cope with this problem, you'll probably have a situation where slow nodes will be not listened to as often, just so the system can make good progress.
Okay, so Andre is saying thank you. Also, I see that Danilo has a question. You can open your mic if you have.
Yes, first of all, I would like to thank you for the very interesting talk. My question is more general, the technical, I would say. So since nowadays we are moving towards smart city equipped with tons of IoT devices having the possibility to run computation and possibly federated learning, what do you envision as services that may move from the cloud toward a federated solution? For instance, I imagine autonomous driving may take advantage of this kind of solution, whereas...
So you're saying what other applications might enjoy or might benefit from
Yes,
federated?
also that nowadays are more on the cloud, but might be more suited to run in a federated learning environment, also to improve the current footprint of these systems.
Yeah, I think the systems that would benefit most would be those where the edge data is more representative of the data that you typically have available to train. So an example of that would be perhaps the best centralized data sets we have right now are things like ImageNet or other ones that are paid for and are carefully curated, and often they might not be actually representative of the deployment situation. So you might have I guess you might have examples of cars that are seen in your data set, but in the deployment locations, cars do not look like that. And so if you if you train your models in a federated style, then your model will be able to will basically be more attuned or personalized to the edge environment in which it lives. The big problem that exists right now is that unsupervised and semi-supervised methods aren't quite good enough yet, although it looks like they might be getting close soon. And so for that reason, federated learning also has this secondary issue whereby the data on the edge also has to be labeled. And so there's not many applications where that is always going to be a good fit. For that reason, things like keyboard models or applications where the user is quite happy to label data, then those are the domains where federated learning is good right now. Another one would be where there's an sort of implicit label. So if you have a keyword, and you're not doing speech recognition, but you're doing a keyword recognition. So something like "Hey Siri" and "Hey Alexa," and then where you know what the person is intending to say, but you want to adapt to, for example, an accent. Then that's another application where federated learning would work well. But I predict that we're not that far away from having advances in unsupervised and semi-supervised methods where this restriction will go away. And if that restriction goes away, well, then the application space of federated becomes really a lot wider. And the importance of having centralized data sets and the relative value against the data on the edge will start to diminish significantly, because you'll be able to train using, you can definitely on the edge, you can collect the data, and that data is definitely going to be more representative of the tasks you're trying to do. So if you have algorithms that can consume that data without being labeled, then suddenly the game can change completely, because it will become almost uneconomic perhaps to shift all of that edge data centrally and train on, if you have an alternative where you can do some computation even at a slower rate on the edge. So I think this is an important part of the puzzle, but it will become incredibly important when other pieces fall into place, things like unsupervised methods.
Oh, okay. So thanks for your answer. Yes, I agree with you that also related to federated learning, there is a fog computing, which is moving basically in the same direction in order to have some preliminary results on the edge in order to avoid all the computing on the cloud, so that it can be better than in terms of either precision and sending less information, either in terms of traffic consumption and so on.
Yeah, definitely. I mean, I think this is compatible with fog and all these other types of paradigms of edge computing. It can be a really important driver for those methods, and complementary kind of those methods that have been come up with in terms of like discovery and sharing of resources are going to fit in very well.
Thank you.
Okay, are there other questions?
Yeah. Hi, Nick. This is Abhishek Chandra from University of Minnesota.
Hi there.
Hi. First of all, a very nice talk. Really enjoyed it. Thank you. I had a question. You mentioned compute and network heterogeneity in your talk. Mm-hmm. Have you also looked at statistical heterogeneity, where maybe the data distributions are different across the different devices and sources, and how does that impact federated learning?
Oh, so that's a great question. And so that's basically something that is out of scope of what we're looking at right now. So we haven't looked at it ourselves, but it's a huge hot button issue for the federated learning community. And they probably even, arguably, it's even more acute than the one we're looking at, because under those situations, the learning algorithms might not converge. You might get, or even worse, you might get a model, but it may have some systematic bias to it, or it may make some really poor judgment because of the spread of the data, and also because when you run these systems, it's often the case that you have very little control about where data accumulates. So because there'll be a lot of societal and spatial and all the other types of factors that come into play in that role. So we have done nothing in that dimension, but there is fantastic work, for example, from that CMU professor. I'm trying to think of his name. I can send you a pointer to his work, but essentially they've been studying the problem of how do you cope with those types of differences between your how the data is aligned across the nodes, and in particular finding what are the tipping points. So what's the distributions do you have at which point, what's the distributions do you have at which point the model starts to behave very degenerately and so on. Phil Gibbons. Phil Gibbons is the guy's name I was thinking of. So Phil, and of course, oh man, my brain is not working so well with names today. But Phil Gibbons has a great paper at ICML this year that speaks about this exact problem. Because one of the key problems in analyzing this situation is that we really lack good data sets that are very representative of the type of data spread that we're going to see in the real world. Only really probably Google has data sets that can kind of give us a sense of those things.
Really? Yeah. All right. Yeah, great. Thanks.
Sure. Thank you.
Okay. Other questions? I still have a small curiosity. When you're computing the carbon footprint of your federated learning system, what's the share of carbon footprint between the data transfer and the CPU for the federated learning method?
Oh, how much is compute and how much is data transfer?
Yes.
So it turns out to be, at least in the models that we have, because I guess I really want to put asterisks on these. It's very situation dependent, and so for what we analyzed, it's the most of the carbon is spent on the compute rather than the data transfer. But that situation could change very easily depending on what you're training on. So, for example, we train on Sapphire 10, and the amount of data you have to exchange under Sapphire 10 is a lot less, for example, than the data you have to exchange if you're training on a more complicated situation like ImageNet. I think ImageNet, we're talking about, I think hundreds of gigabytes of data ends up being exchanged under federated learning. That's one of the big bottlenecks. And so if you analyze that situation, if you analyze the system under that case, I think you probably start to see the data transfer starting to rival that of the compute. What was I going to say? And of course, it also depends on how you're connected and what's the sort of bit per energy joule rate of what you're connected there to.
Okay.
But yeah, Sapphire 10 is a fairly reasonable case because it's a 60,000 images. It's kind of representative of like a kind of a specific task that you might have your IoT system try to perform. But yeah, it's really going to be affected a lot by what you're trying to do.
Okay, so like in the specific plot you were showing the data transfer was like minimal, right?
I think I would say representative of a common IoT task would be what I would frame. So this is your Sapphire 10. I think it's not too. You can certainly have a Sapphire 10 based model, but obviously Sapphire 10 is more of a it's a placeholder. You wouldn't use 60,000 images of. You would typically have 60,000 images of a very specific task for it to work well. Maybe for trying to recognize humans versus bikes versus cars, if you want to sort of record and turn on your smart camera correctly or not. But for that sort of level, you probably could get a decent level of accuracy good enough to deploy. But yeah, once you move to ImageNet, it would be very expensive data-wise, which is why data compression and these other sort of infrastructure and these other questions are really great ones to kind of tackle for a community like this.
Okay, also Andre still has a question. I guess it's the last one because then we have to move to the other session. Andre, if you have your question, stop.
Okay, thank you, Luca. Can you hear me?
Yes.
Okay, great. I'm a little bit concerned about the stragglers being ignored. It suggests to me that there should be minimal performance capabilities or minimum training times for the sake of interoperability in order to prevent federated training from being skewed because some critical device is being ignored. Can you comment on that?
Sure. I think the space for designing those systems is wide open and it's horribly understudied. And the type of methods you just described are ones that people could start to try to look at to compensate. I think probably if you looked at production scale systems that Google are running, they probably have these sort of things sort of hard coded in there, some sort of decisions about what to ignore, when to not worry about a device if it's not responding. it's the Wild West, I think, in terms of lack of study and development of those sort of controls. And so people need to really get in there.
Yeah, I'd be concerned about that for IoT because of safety considerations. Thank you.
Yeah, sure. No, you're dead right. And it's not ready. I think you're right. It's not ready to be deployed unless you have to do sort of bespoke application specific work. You look into the thing you're trying to build and figure out what are the right sort of parameters. But definitely general purpose things. Maybe I would suspect that the understanding in other domains can be migrated. So maybe there'll be quite relatively simple things that could be done to improve the situation a lot better. But you did right.
Thank you.
Okay. I cannot see your questions, so I would really want to thank you again, Nick, for your participation and for the nice talk.
Thank you. The questions are amazing. I really enjoyed the discussion. I hate it when people don't leave time for questions.
Thanks. So we'll be like, I guess, 5 minutes break, and then we can start for.
Yeah. Let me jump in. Sorry to interrupt you. This is Danilo from Milan. I'm the general chair of the conference. So I want to welcome you also to the WAIN workshop. And I want to thank actually Danilo, Luca, Abhishek, and Zili who organized these very, very interesting workshops. So yeah, hope you will enjoy, and thanks a lot for participating to the workshop, to the conference in these days. So you are, in good hands. Enjoy the workshop and what will follow. Okay, bye.
Great.